All right, guys, today we're going to talk about symmetry, mainly on the coordinate plane, but I found some pictures here, actually in your book, of some in nature, and of course railroad tracks aren't really in nature, but some tracks there that I'll show some what symmetry is. Symmetry basically has an axis of symmetry where you can fold it over the axis, and it looks exactly the same as it did, so pretty cool there. Three kinds of symmetry we're going to look at today mainly, and the first two types are on this first big picture up here, and that is called symmetry with respect to the x-axis, which is this first one, and also symmetry with respect to the y-axis, which is the second one. Now the x-axis, notice if I were to fold this parabola over the x-axis, it would match up perfectly. And I want you to notice something else about this thing. Look at the twos. I have a positive 2 and a negative 2, and you know the x's are the same, but the y's, you can have a positive 2 and a negative 2 and it's still the same. This point right here on the y is like a positive, I don't know, 2.5 and a negative 2.5. So the y's can change signs, and that's okay, and it's still symmetric with the x-axis. Now, if you look at the second picture here, just the opposite is true. This one's symmetric to the y because you could fold it over to match up perfectly. But this time, look at the x's. There's a negative 3. Oops, that's a negative 3. There you go. That's a negative 3. That's a positive 3. And they're okay. The point down here that looks like probably about a negative 2.5, a positive 2.5 for my x. So x is going to have different signs, and it's still symmetric with respect to the y-axis. That's how you say it, with respect to. This first one was symmetric with respect to the x-axis. Now the last kind of symmetry is this picture down here on the bottom, and we call this symmetric to the origin because what happens, I could turn this picture upside down, and if I do that, it looks exactly the same as it did when it was right side up. Whenever that happens, that's called symmetry with respect to the origin. And also the difference here is, if you look at the points like we were doing a second ago, the x can be negative 3 or positive 3, and the y's can be positive square root of 7 and negative square root of 7. So this time, the x's and the y's, can change signs, and it's okay. All right, here's the algebraic. Here's how we're going to test to see if a graph has symmetry or not. With the x-axis, we're going to substitute a negative y for the positive y, and if the equation is the same or equivalent, we're going to say, okay, it's symmetric to the x-axis without even graphing it. The y-axis, we're going to do the same thing except with the x. We're going to put a negative x where the x was, and if the equation is the equivalent or the same equation, we're going to say, okay, it's symmetric to the y. And then when we get to the origin, we're going to say, okay, if we replace x with negative x and y with negative y, and we still get an equivalent equation, it's symmetric with the origin. Of course, you can also graph them on your calculator and kind of look at them too, but to be 100% sure, you have to do the test because you can't always trust what you're looking at on your calculator because the graphs aren't, perfect by any means. All right, let's test it here. This first one says test it for symmetry with the x, y, and origin. So all I'm going to do first for the y-axis is I'm going to plug in a negative x. And if I do that, if I plug in a negative x for x, and if I square it, I still get x squared, which is the same thing I had, which means it is symmetric to the x. So I'm going to go ahead and underline that one. It is symmetric to the y. Sorry that I plugged in the x. I got that backwards. You mess up sometimes, just keep right on going. Fix it though. Now to figure out for the x-axis, I'm going to substitute a negative y. If I put a negative y in there and I get that is not the same as what I started with. It's not even equivalent to that, so it's not symmetric to the y. Now, the last thing I'm going to try is the origin. And when you try the origin, remember you put a negative y in and you put a negative x in and see if you get the same thing. Now, this time I would still have a negative over here. If I square a negative, it becomes positive over there. That is not the same thing as this. So the only kind of symmetry that one had was y-axis symmetry. Y-axis only, because the only one that worked was when I plugged in a negative x. All right, let's try the second one down here. Same kind of problem. Let's test it first for the y-axis again. So I'm going to put a negative x in. If I put a negative x in, it's going to be squared again, which means it's going to work. Y to the fourth equals 5. And if I square the negative x, it gives me positive x squared plus y to the fourth. That's the exact same equation. So the y-axis was true. It's symmetric to the y. Let's try the x now. So to try the x, I'm going to put a negative y in. Sorry about that. I'm going to put a negative y in where the y is, and it's raised to the fourth power which, because it's raised to the fourth power, an even power makes things positive, which means that's the same exact equation that I started with, so it's also symmetric to the x. And now let's try the origin. The origin, what you got to do is you got to plug in a negative x and a negative y at the same time and see if, if I square the x, I get positive x squared. If I square the negative y, I get positive y to the fourth. That's exactly what we started with, so it's symmetric to all three, and occasionally that happens. So I'll give you some shortcut tomorrow, not a big one, but that's the test. That's how you test. You plug in a negative x, see if it works for the y, a negative y, see if it works for the x, and plug in negative x and a negative y to see if you get origin symmetry. All right, even and odd, the last thing here. Even functions and odd functions. An even function is just one that is symmetric to the y-axis, which means you do the test. You plug in a negative x, if you get the same thing, it's even. Now, odd is not what you would think, probably. Odd is symmetric to the origin, or two ways you can do that test. One is you plug in a negative x and a y, or if you plug in a negative x, you get the exact opposite of what you started with. Again, you could graph and kind of get a hint on your calculator to see if they might be symmetric or not, but the tests tell you for sure even or odd, and some of them are neither. And let me give you a hint here. This is free. An even one will have even exponents in it. An odd one will have odd exponents in it. But just because that's the case doesn't mean it is even. But that's just a hint, kind of to get you going a little bit. All right. This first one, see if it's even or odd. First of all, the even test is you plug in a negative x. So if I plug in a negative x, first of all my exponents are odd. So I know off the top this is not going to work for being even, but might as well give it a shot anyway, just to show you. So what happens, because my exponents are odd, my negative x's stay negative. So I end up getting this, negative 5x7 plus 6x cubed plus 2x. One thing you can go ahead and pick up right here is if you plug in a negative x, what the signs that are going to change are going to be your odd exponents. Your even exponent signs are not going to change. So because this is different from what I first started with up here, it's not even. Now to check odd, I'm going to put in a negative x and see if all the signs change. Now, I already put in a negative x. Did every single sign change here than what I had up there? Is it completely the opposite? And the answer is yes, it is. And because they're all opposites, that means it is symmetric to the origin, which means it is odd. That one is odd. And the hint is, look at the exponents. They were all odd. That will not always be the case. It depends if you have a constant or not. But it's a good hint, at least what you're looking for. Okay, the next one. Next one kind of looks even to me because I have even exponents, but you got to check it out. So what I'm going to do is I'm going to put a negative x in for the x's and see what happens. Now, for it to be even, I've got to get the exact same thing. So when I plug those in, I get an even exponent makes that positive, an even exponent makes that positive, and I got a minus 7. Now, is that exactly the same thing we started with? Yes, it is, which means it's even. Now, if it would have been odd, this number, the expression I got down here at the bottom would be exactly the opposite of what I started with. And it's not exactly the opposite, it's exactly the same thing. So that means it's even. If it's even, it's the same thing. Odd, it's a complete opposite. All right, so there you go. Shouldn't be too bad at all. Just a day of symmetry tomorrow. I hope that made sense to you, and I'll see you tomorrow.